First of all, I would like to express how glad I am to be here, and I see many beautiful and very interesting things. And but I won't. I could speak hours about that, but I would rather speak about my field, combinatorial optimization. I try to give you an overview of what we are doing, what our colleagues were doing in the past years, and what our field looks like today. So, what is combinatorial optimization? If I wanted you to leave the room immediately, then I would give this definition. It is about minimizing or maximizing a function on a finite set or on a 0-1 set. These things are all equivalent. Of course, there are many interesting things about how the function is given and what is the content of this problem. So this definition is really not interesting. It is not only boring, but not completely true like that. So I would rather tell you what we are doing on some concrete examples. Well, first of all, if you haven't yet met concrete problems of combinatorial optimization, let me tell you two problems. First, the Postman problem, but you can forget about the adjectives. The Postman problem and the Salesman problem. In one of them, the postman typically wants to cross the streets of a town, and each street of a town at least once. But sometimes he has to go through some streets several times, just because he can't fly, so he's obliged. But it's enough, so his duty is to go through every street at least once. And in this case, the vertices denote crossings of roads, and the edges, this is a graph which consists of vertices and edges that join the vertices. This is an abstract thing, so we don't care how these paths go. We care only what are the pairs of vertices that are joined by edges. And the salesman has to go through every town exactly once in one formulation. Actually, it's equivalent to say that at least once, but that's also something we don't care about today. And there the vertices of the graph, so the nodes, the points, these are all synonyms, represent towns, and the salesman has to visit each town once. Now, if you hear about these problems for the first time, and you have to minimize for each the paths that the distance that they walk or drive. If you listen for the first time, are there among you who hear about this for the first time? I hope, because I would like to ask you to vote whether, well, these two problems don't have the same difficulty. One is tractable, the other is provably non-tractable in some sense. So for the other, you can prove that if you could solve it, you could solve many other fantastic things, and one of them, there is a solution for quite big sizes. Those who don't know the problem, who would think that the first one is the difficult one? Oh, everybody knows the problem, that's why. And who thinks that the second one is the more difficult one? Okay, everybody knows yes, you would think the second one is the more difficult one, but you know the problem. Hojin, I know you, so you know the problem. That's indeed the case. So the second one is the difficult one, and that determines the approaches you can use for them. The mathematics are completely different for the second one as for the first one, and I would like to give you a feeling of what you have to learn, at least in order to be able to decide these things. So in order for these two problems to be clear, this is what the postman does. Now, he didn't do yet all the streets, so in order to do all the streets, he had to use twice an edge. Now he has to use this again, because there is still one street left. And now, in order to go back to the post office, he has to use a third one. second time, and the salesman does every vertex once. So these are the two problems. Actually, this is one of the most ancient problems in some sense. A special case has been treated by Euler, who solved who solved when exactly you can cross every row, when the postman can go through every street exactly once. But the question was asked in terms of bridges. If you look at old graph theory books, you will see the problem stated in this way: the bridges of Knigsberg, where the citizens of Knigsberg asked the mathematician Euler how could they go through every bridge exactly once. But you also met the problem with your children when they had to draw a house or some drawing, not taking their pencil from the paper. If you give them a graph where it is impossible, you are quiet all the afternoon. You won't be bothered, but it is quite cruel. This is the graph. I just put it there. And in order to now, by what Euler realized is that if you have an odd number of vertices like we had before, an odd number of edges incident to some vertices, incident to too many vertices, here there are 4 vertices with an odd number of edges incident to them, then you cannot solve the problem. In order to solve the problem, you must have only at most 2 vertices of odd with an odd number of edges incident to them. All the others must be even. Even if you want to go back to the same place, all the vertices must have an even number of edges incident to them. This is quite easy to... What happened? I pushed the wrong button anyway. Okay. So you have to go twice, but if you put 2 edges one more times, then you have an even number of edges and you can go through. So this is Euler's theorem. And now, after this introduction, let's see what is our future for the following hour. I will tell about 7 problems. We'll use the metaphor that these are animals that we are dealing with, and the methods, ideas are our flora. So this is in order not to have this formal definition, but to put a population, to give some content of what we are doing, to have some examples. So this is the flora and the fauna. And on the second floor, and this is a point I would like to make in this talk, that recently we are ourselves solving and seeing at conferences many problems which are more complex than just one nice theorem or one nice algorithm. We have complex problems that use several of the methods that were explored at the first floor. So I would like to show some examples that I've met recently, which are like that, and we'll make a zoom on each. So some problems we'll see in more details. So let's see the zoom of the first floor now. Here are the books. The somewhat end period of this first time, of this first era, is shown by Schreifer's book, which is the yellow book in 3 volumes, quite the Bible of our field, which shows all the basic problems, how to solve them. That's what we refer to when we want to look up something quickly. And there's an even more recent one by Frank, which is a bit more specialized, but also for some problems. This is a basic book, and Lovaas Plummer about matchings, which is one of the most important objects that we are dealing with. I will tell you what they are. So, first problem. I am now starting to say a few words just about these 7 problems to see what kind of problems we are looking at. The Postman problem, we already defined it, we mentioned it, so I will be short. I mentioned shortly that we have to double edges to satisfy Euler's condition, but here, since the postman wants to go back to the post office, these are the 3 red edges that we double, and then every vertex will have an even number of edges, and we satisfy Euler's condition. So this is a solution, and probably the minimal solution in Euclidean distance if the edges really are on the map like they are drawn on my figure. And this problem is tractable. There are theorems which show why there is no better solution than what we found. There are good algorithms. This is part of matching theory. And actually at our course we'll discuss it in details. And also at the discrete mathematics seminar. So other matchings. Another basic notion. So a matching is in a graph is a set of vertex disjoint edges. So an edge has 2 vertices, and the vertex disjoint set of edges is called a matching. And find a maximum matching or minimum weight matching is also one of the basic problems that we are dealing with, and also there are nice theorems and nice algorithms that treat them. Now, the flora methods, linear programming is one of the methods, and also matchings. For matchings they help, and they are present in the methods and in the theorems. Linear programming, which is a set of linear inequalities, and you maximize a linear objective function on these constraints and these linear inequalities as constraints. What we like is to have a geometric characterization in order to be able to use linear programming to take the convex hull of incident vectors of the objects we are studying. For instance, for matchings, we take the incidence vectors of matchings. They are 0, 1 vectors. We take their convex hull, and we want to describe them with linear inequalities. Now, why is it good to describe with linear inequalities? It is good because the classical use of it is because then you know a reason why your matching is optimal, or you know why it doesn't exist. Linear programming has tools to show this, but a new way of using it, which I will show on some examples, is called randomized rounding, and there are many variants of it. It means that a convex combination, as you know, it's a sum of lambda I times the objects you take the convex hull of, and it can be interpreted as a probability distribution because the sum of lambda i's must be 1 in a convex combination. Now, if the sum of lambda i's must be 1, then the lambda i's can be interpreted as probabilities, and so you choose a matching, you choose an object with that probability, you take such a random variable, and then what you combine with a fractional vector will be the expectation of your random variable. And this, sometimes you can use deep probability theory, sometimes it's just a notation which helps you thinking about the problems. And actually the fact that you use often about them is that the minimum of the object you take the expectation of has smaller objective values. So, for instance, for a linear function, the minimum on your object is smaller than the expectation, which it's a very simple theorem because in some contexts it is less obvious. So in linear programming this fact is called that if there exists a solution, there exists a basic solution in geometry, Kara-Theodoris theorem. Okay, so an example of this use, a very simple example that was actually one of the exercises in the exam that the students in discrete mathematics had in some version, some little bit more general version of it. I will show it on the 3 houses, 3 wells example. You can observe the following. There exists a pairing of length at least 1/3 of the sum of the distances. So you take the sum of the distances between 3 houses and 3 wells, And then there exists a pairing, so you can choose which house belongs to which well, in such a way that the pairing you have chose has at least 1/3 of the distance. It would be more natural to say at most, but then it's very obvious, the example, so why not at least for some reason. Now, what a well is, it's not in my active vocabulary, so I was afraid that you won't know. This is a well, and for younger people, this is also a well, and I looked up how in Korea, also in Japan, I wanted to know how in Asia the wells look like, and for Korea, what I found under wells is this. So maybe you didn't have wells, but or the water supply was always coming from the sea. I don't know. Anyway, the little bit more generally, this example says that if you have a weighted bipartite graph and every edge is incident to exactly 3 edges, then 1/3 of the total will exist a matching with 1/3 of the total weight. And the linear programming characterization we wrote down shows that this is true, because if you take the 1/3 vector, it satisfies the inequality. So this is why it's good to have the inequalities. The 1/3 vector satisfies the inequality, so you know it is a convex combination of matching. So it's know the average of some random matching valued random variable. Okay, and now let's go to an example of the fauna linear and semi-definite programming, our methods used. They progressed in the past years. With semi-definite programming, I will stop a little bit. That's a generalization of linear programming. And, okay, but first 4. Matroids, that's some kind of special family of sets. A matroid satisfying some axioms. Okay, I don't want to spend much time on it. There are many examples of naturally arising hypergraphs, that is families of sets, that satisfy these axioms, and so general theorems that you state about them will be applicable to interesting special cases. Okay, I would like to go to this semi-definite programming example because that's the origins of it are simple to explain. Lovász's celebrated result on the Shannon capacity, which was a conjecture which was open for some time. So you have to transmit some characters, 5 characters actually. Shannon's original problem was about 5 characters. You would think discrete mathematics, many people used to classical fields of mathematics say it's finite. Here, not only finite, but 5. It's about 5 things. You have 5 characters that you have to transmit. It's not A, B, C, D, E, because I wanted characters that you can confuse. You can confuse A with C, V with W, U with V. So the neighbors, the neighbors on this, this is called C5 graph, 5 cycle. Those which are neighbors there, they can be confused. So if you transmit them, you can't be sure that people will read. It's not a good idea to transmit, for instance, U and V, because they will not be sure. Some people write a U like a V. They will not be sure what you transmitted. So how can you transmit a meaningful message with these characters? Well, if you can transmit 1 letter, what would you do? How can you transmit a meaningful, how many different messages? That's what characterizes the amount of information you can transmit. How many characters which are not confusable you can transmit? Well, if you are allowed to transmit just 1 letter, you will choose, for instance, C and V, right? They are not confusable, C and V. So you can transmit 2 different messages. So 1 bit like 0 and 1. 1 bit of meaningful information you can transmit. So for 1 letter, it is 1 bit that you can transmit. So of length 1. That's the answer is you can transmit 2 letters, which means like if you had 0, 1, so this is 1 bit. Even if we don't define precisely the measure of information, you can understand it is 1 bit of meaningful information. Now, of length 2, what can we do? Now, of course we can, if we, with 1 letter we can transmit 1 bit, with 2 letters we can transmit 2 bits at least. But can't we do better with 2 letters? And that's what's surprising, and of course that Shannon knew that with 2 characters you can transmit not 4 different letters like you would do if you just repeated the 2 different letters that you can transmit at one with one by using twice 1 character. You can transmit 5, not only 4, so 1 more. Okay, now the conjecture was that you can't do better. Even if you choose arbitrarily long, no matter how long, you can't do better than in average transmit log 5 over 2. So this means what we have done so far, that is log 5 over 2 per bit is the useful information. It's like if we had square root of 5 characters, not 2, but a little bit more, because with 2 characters we can transmit 5. It's like if we have square root of 5, a little bit more than 2 characters. And this was a conjecture for a long time until Lovász proved it in 79 using orthonormal representations of vectors of vertices of a graph. An orthonormal representation means that you represent, you put a vector in every vertex of the graph, and if they are not joined by an edge, then they must be orthogonal. And this gives a valid inequality, just a linear inequality, which is valid for all the stable sets, so subsets of the vertices which are not joined by edges. And this led to the definition of theta body and of semi-definite programs that became a whole field, which is very much used today. And anyway, first it solved so this is an orthonormal representation. It is an umbrella. And with the help of a very simple inequality with tensorial products, you get that if you take a graph which has in each if you multiply your graph, so you take the Cartesian products of graphs and you define the stable sets appropriately. A stable set means that you can't confuse the 2 words. So for words of size k, if you don't confuse k words, you don't join them with an edge, and the orthogonal representation for 2 yields you an orthogonal representation for arbitrary length sequences, and with the help of this you can have inequalities for arbitrary length sequences, and you can prove Shannon's conjecture. Okay, now 6, cut. Cut is a basic notion that arises a lot in applications as well. And it is the set of edges that go between 2 classes of a partition of the vertex set of a graph. Okay. Now here again I could make you vote which one is more difficult, minimum cut or maximum cut. For those who don't know the problems, is it minimum cut? Is it maximum cut? Again, you know very well both problems, so that's why I had this constraint that those who know shouldn't tell. So minimum cut is for non-negative weights is a problem that can be treated, and maximum cut is one which cannot. NP-complete means that we cannot unless, well, I won't be precise, but it means a negative about the tractability of the problem. There is a simple algorithm which 2 approximates, which means that always finds at most twice the optimal solution, and it is just to flip a coin and make in the 2 classes and put in the 2 classes of the partition according to flipping a coin your vertex. This in average will be at most twice the optimum, so the best of it will be at most twice the optimum. And actually you can de-randomize it, or you can directly find the direct algorithm. You always put the edge in the class where the total number of the sum of the edges is smaller. Now, this is a very important problem that many people looked at it and developed semi-definite programs as well. It was a very big result of Goemans and Williamson that used the geometric ideas, semi-definite programming, and randomization that always finds not the maximum cut, because that's hard to find, but at most 0.878 times the maximum of the cut. Another problem for which approximation, and of a different kind, but still in the form, if you wanted, we could write it in the form of that first boring slide. It is a combinatorial optimization problem to put objects into bins. So you have equal bins, say, and you have different size objects, and you want to put your objects in such a way that you use the minimum number of bins. Now, very simple algorithms give here also, this is an exercise that some combinatorial optimization courses, that if you just put at the first bin where an object can be put, that's already a 2 approximation algorithms, and then you have a little bit more sophisticated algorithm. You can go until 11/9 with simple ideas, and then with more difficult ideas, actually, you can have for arbitrary epsilon and epsilon approximation for this problem. Okay, now we have filled in our zoo, our fauna. We have some problems, and the message I would like to give that, quite interestingly, these problems tend to polarize. So some of them are difficult, some of them are tractable. There is rarely a third case. And then the methods you use are polarized into directed optimization, which is related to directed graph, and it has a general algorithm, which is called metroid intersection. So it's about metroid, which contains most of the directed optimization problems that you have in your hand, sometimes requiring new ideas, but the kind of methods you will use will belong to this directed optimization. And then some other problems you will have to treat with parity arguments, like we had for the Chinese Postman problem or for matchings, and you will have to use other kinds of methods mainly. And in the intersection of the two, there is bipartite matching. So finally, there are not so many different main stream problems at this first level. And it became a theory. That's what, of course, not a simple theory. That's what Schreifer's 3-volume book is about. And so, I don't know whether I succeeded to give an impression of this first floor, but anyway, we go to the second floor. So we will try to see some problems which use several of these problems. Okay. And which are often related to applications. They arise from some applications, then mathematicians are interested in the problem itself. But the theory, while it is being developed, often it can feed back to the applications, and some of these are really applied. So we do the focus. There are some recent books about these. They are more recent than the others, of course. I like very much both books, actually. Lau, Ravi, and Singh's book on iterative methods in combinatorics, and Williamson and Schmoy's book, The Design of Approximation Algorithms. They contain several problems which are of this kind, which use several problems at the first floor. The first problem, which I know a bit better than the others, is the VPN problem, which comes from the VPN. When you connect from distance or connected in the old days, then you had to use VPN. And computer scientists formulated what kind of problems this leads to. And this leads to the following problem. You have a graph, you have terminals, and you have a cost function. And also a capacity function on the vertices, and you have to buy capacities of edges. So it's a bit different, it's a bit twisted to what we are compared to what we are used to. You have to buy capacities, and what is required from you is that you have to give in advance the paths on which you want to make a routing between the vertices so as to satisfy the demands for every vertex and so as to buy as little capacities as possible. I don't think you can feel the problem with such a short definition. It's just to listen to the music that this is a new kind of problem that comes from some network design application, and the solution that was first given is by optimizing the minimum of two objective functions which had a pyramidal form, so it was called the pyramidal solution. And finally, what could be remarked is that you don't need actually this pyramidal function, but so you don't need pyramids, and actually some mysteries which were about the existence of solutions to that problem were just related to the existence of basic solutions, so to this easy fact from linear programming or geometry or probability theory that if there exists a solution, there exists a basic solution, and you could characterize the polyhedra, so optimize arbitrary weights for this problem, as we have proved. And the message that I would like to give with this is that, well, this was a first example for me in my own experience where we used several problems. We used some methods from directed optimization from that picture that I gave from the first floor of the problems. We used multi-flows, flows, linear programming, but also B-matchings and matchings. So some problems from the parity ideas, from the other pole of optimization. Okay, the second one. Well, it's not the second one is just a summary of what kinds of methods are very often used. Linear programming, semi-definite programming, like we saw in the Shannon capacity, extended formulations where there are also negative results, where algebra and analysis are used, randomized rounding, entropy methods. So sometimes in this probability distribution you choose one which has the maximum entropy, so information theory comes into the game. Actually semi-definite programming is twice. I tried to cheat, but I didn't succeed. I saw that you were laughing. So this is about the flora, and in the fauna, well, you have many notions that I wrote there, those that we mentioned, T-joins, matchings, metrid partition, metrid intersection. And many problems, more and more problems, use several of these nowadays. Okay, I will not speak about the others. So the third example, let us, and actually second example to which I was and I am still related to, I will speak about that in more details, more technical details, at the discrete mathematics seminar, is the Travelling Salesman problem. Why is the Travelling Salesman problem so important? Well, it is a sample problem. So why problems become sample problems is because they are simple and they can be used by other problems. So the 7 are quite typical ones, and there are not many more, maybe the double or 3 times those basic problems that we use all the time. But also in applications, the traveling salesman is not because we have many traveling salesmen who travel through cities, but what is it about, the traveling salesman? It's about orders, right? We want to order of visiting towns, but it can be also more abstract things, or for instance, so it can be the abstraction of several other things. For instance, production processes. In what order you want to execute on one piece of material, several processes, and you have some cost to pay when you transit from, when you switch from one procedure to another, and you want to, but they can be, it's commutative. You can execute your jobs in the order you want, but the cost is different. So if you want to determine the order, it's a traveling salesman problem. The traveling salesman problem doesn't have to define Euclidean distances. Then you put your edge weights on the edges of your graph, the transition costs, and you want to minimize the order. You want to determine the order which minimizes the sum of transition costs. This is also a traveling salesman problem. So it arises a lot also. Okay. Now, the linear program that you can define for it relaxes, finds also fractional solutions for the traveling salesman problem, and it is the following. For every cut, you want to be intersected by at least two edges. So you want variables to sum on every cut, variables on the edges to sum on every cut, to have a sum at least two on every cut. And in this process definition, and also for the direct first traveling salesman problem, it is interesting to have two special vertices, not necessarily arrive back to the same vertex from which you have started. So we allow the salesman start from a vertex and arrive to another, and go through every town exactly once. So cuts which separate S and T, we only ask that they are intersected at least once, because that's what dictates us the traveling salesman problem. The integer points of this polyhedron or polytope are indeed the Hamiltonian paths, so paths that go through every vertex exactly once. And the optimum is the integer optimum is the minimum Hamiltonian path length. When you relax this constraint, when you relax integrality, you get to a fractional solution satisfying those constraints. So now, the interesting thing is that the linear programming relaxation in this case is related to both of the things that you actually want to satisfy. One of the things you want to satisfy is connectivity. It's already in Euler's theorems, the two are present, right? In Euler's theorem, you have the graph to be connected in order to go through the bridges of Knigsberg, and you need a parity constraint. So you need connectivity and parity. But the fractional solution already gives you little bits, something towards both. Because by knowing metroid theory, and this is already a precursor of using several things from several parts of optimization, you can prove that the fractional solution that you get from this linear programming relaxation is a convex combination of spanning trees, of trees connecting all the vertices of your graph. So any solution satisfying the linear program will be a convex combination of spanning trees. That is, a spanning tree valued, it will be the expectation of a spanning tree valued random variable. On the other hand, the half of this vector from a result of Edmonds and Johnson, which is also on the first floor, so we go down to the first floor to buy some of the results that have been developed there, you get that half of a solution of such a linear programming solution will be in the convex hull of objects that correct your parity, that make your graph Eulerian, which are called T-joins. So if you add up the two, then you can solve your problem. So with at most 3/2, what's happening? So with at most 1/2 more than the optimum of your fractional solution. So the weight of your fractional solution is a lower bound for the integer solution. It's a relaxation. If you add half of it, you can correct the parity. So with 3/2 times the linear programming solution, you can correct the parity. This is called the integrality gap. You have an integer solution with 3/2 times the value of the fractional solution. Now, at the seminar, I will tell the details how you can go further, how you can, with randomized rounding and de-randomization, with the help of going a bit deeper in about facts to teach on just on purpose of this problem, also deleting edges, not only adding for correcting parity, also doing some randomized steps, but defining the probabilities with the help of a linear program. So going to a little bit more sophisticated direction and using matroid intersection and matroid partition from the first floor again. So using several things from the first floor, you can improve these results. And the improvement doesn't concern the general case when the salesman has to go back to his original place. Since 76, there is nothing better than Christofides heuristic. On the other hand, recently we could, and actually before us, I will show on the following transparencies, since 2010 there are improvements, and I show only the last results, which are 3/2 if your metric is special, modeling only, modeling mainly this scheduling special case when every edge of the graph is of length 1. If every edge of the length is 1 and you take the metric generated by this, by the cardinality of paths in your graph, then you can have a 3/2 bound even when S is not equal to T. And when S is equal to T, you can have a 7/5 bound on the problem. You can have a minimum 2-edge connected graph. So if you want reliably join your graph so that deleting any edge it is still connected, you can have a 4/3 approximation of your problem. The red ones are the best in terms of integrality gap. So there it is mostly accepted, even though precisely not true, that they are the best results. The red numbers above mean that those are the conjectured values, so those are not best possible, and probably someone will come. And there is quite a big competition in this, and it will improve this result. And the last one dates from the beginning of this month. We have finished and put on the archive our paper, which solves the problem, but this is wishful thinking that I first put 3/2 there. That's what we would like to prove. For when S is not equal to T, we also have a 3/2 approximation algorithm, but we have 1/34 worse. So if somebody is interested, can look at our paper and try to find. That would be a really important result, even though the difference is only 1/34, but to get a 3/2 approximation for the ST tour problem when S is not necessarily equal to T. This is what I will explain at the district mathematics.
Not an additive.
That's what we prove. We prove only 3/2 plus 1/34
Times
of the optimum. Yes. Okay, so this was, for some reasons, there was more than 20 years of stop here, and things started in 2010, 2011, and that's when we proved the results. For the moment, we are partly with Jens Figen, partly with Anke van Zijlen. We have the best approximation ratios, but I'm sure it won't last for long to be the champions. So this, at the same time, just about the traveling salesman problem, we had algorithms which approach the postman and the salesman, so they became quite close. Because we use the postman, the solution for the postman, the idea is there, we use for the salesman. So for a more difficult problem, we use some other things. This is not the end of this problem. As you saw, there are many. For instance, in the last result, there is something too big, and then there are many versions which are still open, and the most important conjecture when S is equal to T, the 4/3 approximation, is also open. These were just examples, and the field, like any field of mathematics, when you solve a problem, you have ideas to progress, to make progress, to raise new problems. So who knows what will be. These were the two floors. I tried to give an impression of them. Who knows whether there will be a third floor or not, but probably there will be, and it is up to some of you to build following floors, and also to make little progresses also on the first floor. There are some holes, even though it is a little bit closed now, so the main methods, the main directions are clear, but there are still some holes which are quite nice and which have a quite high value if you solve them. So thank you very much for your attention, and I'm glad to have finished in time.
Thank you. Do you have any questions?